Thanks very much for spending a few minutes with me to learn some ways in which Bayesian methods interpret data better than null hypothesis significance testing. In Bayesian data analysis, the role of data is to reallocate credibility across possibilities. The possibilities are parameter values in a model, such as the mean of a normal distribution. We reallocate credibility to parameter values that are consistent with the data. Here is a realistic example of Bayesian analysis for comparing two groups. The data are shown by these red histograms. As shown here, Bayesian analysis produces a complete posterior distribution of credible parameter values, including the difference of means, the difference of standard deviations, and the effect size. The distributions indicate the probability density or credibility of all possible parameter values given the single fixed data set. Let's zoom in on the distribution for effect size. A good way to summarize the spread of the distribution is with its 95% highest density interval, abbreviated HDI. You can see it marked by the horizontal black bar. Any parameter value inside the HDI has higher credibility or probability density than any parameter value outside the HDI, and the total credibility of parameter values inside the HDI is 95%. Sometimes researchers want to decide whether a difference of 0 is credible given the data. Our decision rule involves a region around 0 that includes differences that are equivalent to 0 for practical purposes. In this example, I chose a region that goes from negative 0.1 to positive 0.1 because an effect size of 0.1 is conventionally called small. The figure has this region of practical equivalence, or ROPE, marked by red vertical lines. For this example, notice that the 95% HDI falls completely outside the ROPE. Therefore, the 95% most credible values of the parameters are all not equivalent to 0 for practical purposes, and we decide that a difference of 0 is not credible given the data. The decision rule also provides for accepting the null value. For the large samples of data shown by the red histograms here, the resulting posterior distribution is very precise. The posterior distribution shows that the 95% HDI falls completely within the ROPE. Therefore, we accept a difference of 0 for practical purposes because the 95% most credible values are all practically equivalent to 0. A full explanation appears in an article in JEP General. Free, easy-to-use software and information are available at the website shown here. All of the preceding was background explanation for how Bayesian analysis works. Now we will look at 3 of many ways in which Bayesian analysis interprets data better than null hypothesis significance testing. Many other advantages are explained in the article. One advantage of Bayesian analysis over null hypothesis significance testing occurs when analysts conduct sequential testing. After every new datum is sampled, a new test is performed to see whether the HDI excludes the ROPE. This graph shows an example of sequential testing for simulated data from the null hypothesis in which 2 normally distributed groups have identical means and variances. With each step, one more random datum is appended to a group, alternating between groups, and a Bayesian analysis is conducted. The horizontal axis plots the total sample size of the 2 groups. At each step, the 95% HDI on the difference of means is plotted as a vertical bar. In this example, the 95% HDI eventually falls completely within the ROPE, and the null is correctly accepted. Suppose we conduct a traditional t-test at each step in the sequence. The lower graph plots the p-value for each test. NHST has no way to accept the null even when p is close to 1, and NHST falsely rejects the null at steps in the sequence around a total sample size of 100 because the p-value was less than 0.05. The Bayesian decision procedure can also produce false alarms, of course. The upper panel shows a sequence of randomly generated data from the null hypothesis, such that eventually the HDI falls outside the rope, and the null is falsely rejected. The lower panel shows the same data analyzed by NHST, which also falsely rejects the null, but much earlier in the sequence. In fact, NHST will eventually reject the null under sequential testing, even when the data come from the null hypothesis. The graph plots the proportion of sequences in which NHST falsely rejects the null as a function of sequence length. The red curve for false alarms essentially rises linearly on the logarithm of the sample size. NHST has no way to accept the null and will eventually produce 100% false alarms. In the Bayesian approach, the probability of false alarm asymptotes well below 100%. Essentially, once the sample is large enough, the HDI cannot fall outside the rope, and false alarms can no longer occur. If we collect enough data, the HDI will eventually fall inside the rope, correctly accepting the null. Thus, when researchers conduct sequential tests on data as they accumulate, NHST runs a higher risk of producing false alarms than Bayesian methods. A second advantage of Bayesian estimation is that it facilitates the goal of precision in estimation. A good way to measure the precision of a parameter estimate is by the width of the 95% HDI of its posterior distribution. As sample size increases, the precision tends to increase. This is often a better goal than rejecting the null value. For example, in election polling, we want a precise estimate. This goal is easy to pursue in Bayesian analysis, but not in frequentist approaches. For example, a frequentist confidence interval on the difference of means can become huge merely by intending to conduct other tests. A Bayesian HDI depends only on the actual data. Bayesian power analysis for this goal is straightforward. Explanation and software are provided in the JEP Journal article mentioned previously. A third example of the advantages of Bayesian analysis over NHST comes with multiple comparisons. As an example, consider estimating the batting averages of professional baseball players. For each baseball player, the observed batting average is the proportion of hits out of the total number of opportunities at bat. Here, we'll consider 351 players with between 1 and 655 opportunities at bat during the 2012 regular season, from a total of 10 teams, 5 each in the American League West and the National League West. There are many comparisons we may want to conduct. How different are particular players? How different are particular teams? How different are the divisions? Making multiple comparisons in NHST is problematic because the criterion of NHST is to keep the overall false alarm rate capped at, say, 5%, and every comparison is another false alarm waiting to happen. Therefore, as the number of intended tests increases, the critical P for declaration of significance must get stricter, and consequently, analysts perform as few comparisons as possible. They rationalize why only those few comparisons were conducted, and they feign disinterest in other aspects of the data. By contrast, in a Bayesian approach, the decision process is not based on a space of possible outcomes that grows with each test intended. Instead, Bayesian decisions are based on the single posterior distribution from the one set of actual data. In a Bayesian approach, it's easy to analyze a hierarchical model for describing these data. At the bottom of the diagram, the data consist of the number of hits and at-bats for each player. For each player, there is a parameter theta that describes his underlying probability of getting a hit. And at the overarching level, There's a parameter mu that describes the typical probability of getting a hit across all players, and a parameter kappa that describes the variance across players. Bayesian analysis provides a complete distribution of credibility across the joint space of 353 parameters. To compare the abilities of players or teams or divisions, we simply look at the posterior distribution of the relevant differences. Let's compare two individual players, Buster Posey and Nick Hundley. The players' sample batting averages are indicated by red crosses on the x-axis, and the Bayesian posterior distribution for the estimated probabilities of getting a hit are shown by the blue distributions. Notice that the Bayesian estimates are not centered over the sample value. Instead, there is shrinkage of individual estimates toward the group average, which falls between these two players. Hierarchical models produce shrinkage because the individual estimates are informed both by the data from the individuals and by the data from 349 other individuals via the overarching group estimate. The posterior distribution on the difference of the individual parameters for these two players shows that the 95% HDI excludes a reasonable rope around 0. Here are two players with very similar records. Michael Saunders got 125 hits out of 507 at-bats. Cameron Maben got 123 hits out of 507 at-bats. The posterior on the difference has mean essentially at 0, and its 95% HDI falls completely within a rope from negative 0.05 to positive 0.05, which represents a difference of only 5 hits in 100 at-bats. We declare that these two players have equal probabilities of getting a hit. Here are two players with very few opportunities at bat. David Hernandez had 1 hit in 1 at-bat. Even though he had a batting average of 100% in this sample, the Bayesian estimate of his probability of getting a hit is broadly spread around 0.247, nowhere near 100%. This is because the group information overwhelms the tiny amount of data from this player. Robbie Ross had 0 hits in 2 at-bats. For his sample of data, the batting average is 0. Yet the Bayesian posterior shows a best estimate broadly spread around 0.238. Even though one player had a batting average of 100% and the other player had a batting average of 0%, the Bayesian estimate of their difference is centered at essentially 0. The HDI is very broad, however, because there are so few data from these players. We can also make team-level and division-level comparisons. In the left column, we take the average of the individual estimates for players in the Los Angeles Angels and the average of the individual estimates for players in the Seattle Mariners. The middle column compares the Angels and their crosstown rivals, the Dodgers. The right column compares the National League West and the American League West and shows that they are virtually identical. Notice there were no corrections for making these multiple comparisons. The conclusion from each comparison is unaffected by the intention to make other comparisons. This is because there is only one fixed Bayesian posterior distribution from the one fixed dataset. Each comparison is merely a different perspective on the single joint distribution. Bayesian multiple comparisons can suffer false alarms, of course. No analysis is immune to false alarms, because data are random and accidental conspiracies of rogue data can arise. But the Bayesian posterior distribution is the best inference we can make given the data we have. Bayesian hierarchical modeling diminishes false alarms by letting the data inform shrinkage of estimates. Non-Bayesian hierarchical models also produce shrinkage, but NHST decisions require difficult defining and deriving of sampling distributions from null hypotheses for determining p-values, which change depending on intended comparisons. And attenuation of false alarms from hierarchical modeling does not use the intentions on which NHST relies. There is no notion of planned comparisons versus post hoc comparisons, and there's no counting of intended comparisons. In summary, I've shown 3 ways that Bayesian methods interpret data better than NHST, and you can find lots more info in the textbook. Thanks very much for your attention.